Hello and welcome to week 6. Here we take a bit of a departure from the theme of designing algorithms for problems to talking about problems in a more general sense. So we are going to begin by talking about how problems are classified into broad categories based on their computational complexity. And most of this week will be about coming up with reductions that relate these problems to each other. So if you have already done PDSA, you have probably stopped with NP-completeness and the notions of the complexity classes P and NP, and you've probably seen a couple of examples of reductions. So we're going to basically pick up from where we left off. If you like, maybe revising some of that material would be a good idea getting into this week. And we'll do a quick review of complexity classes in this introductory video. And from here, we are going to go on and actually look at examples of a few reductions in the remaining videos to come. So to begin with, let me just recap what we did in the last week, where we used network flows to solve other problems. And we've seen a bunch of different problems that didn't even necessarily look like graph problems, forget network flow, but we still managed to take those problems and transform them into instances of network flow in a meaningful way. And by meaningful way, I mean that transformation was such that solving the network flow instance generated by that transformation basically amounted to solving the original problem itself, which made that transformation extremely useful. So what we did was we started with an arbitrary instance of the problem that we wanted to solve, and then we reduced it to an equivalent instance of the network flow problem. So this is an illustration of using the technique of transformation to solve problems by leveraging known algorithms for other problems. But this week, we are going to flip the script and we are going to start with some problem that we know is not easy to solve. In fact, we are going to start with problems which have a lot of history and problems that are believed to not admit efficient algorithms. So we're going to start with problems like that. And we are going to reduce those to problems that we care about, problems that we are trying to solve. Now, what impact does such a transformation have? Well, it certainly doesn't solve our problem, right? Because we are, first of all, involving a problem that we don't know how to solve, and then we are reducing that to our problem. But what this does reveal about our problem is that it's at least as hard as this problem that we started out from. And if that problem is widely believed to not admit an efficient algorithm, then that belief should now carry over to our problem as well. Because if there is indeed an algorithm that can efficiently solve our problem, then that algorithm can actually also be used to solve this hard problem, in the same way that we leveraged flows to solve a bunch of other problems. So now, if you have an algorithm for problem X here, then you can use that algorithm to solve problem Z by basically chaining this reduction with that algorithm, right? So if you have a sensible reduction and a valid algorithm, then these two pieces can be combined to solve the bigger puzzle of solving problem Z. And if problem Z is a sufficiently notorious problem, then you would imagine that from this we can conclude that problem X can now also claim the same notoriety, saying that, well, now X has the same status as the problem Z. It's just as hard to solve. So this is something that's useful to do when you're stuck on a problem and you really believe that it does not probably admit the kind of algorithms that you're looking for. Then you try and find ways in which you can position it in the same class as other problems that are also known to not admit polynomial time algorithms, right? So that's a lot of what we will be doing this week. We'll be trying to prove that the problem X, the one that we are interested in, is as hard as the problem Z. So that's what we will be doing most of this week. We will be starting with problems that we suspect are hard, and we will be reducing them to problems that we are stuck on, and we're sufficiently stuck on them that we believe them to be hard as well. And we are going to make that belief more formal by establishing these connections. Notice that when you're working with reductions, and let's say that we have this informal classification of problems into easy and hard, these words don't have formal meanings at the moment, but for the sake of discussion, bear with me. Let's say that a problem is easy if it's a problem for which you know that you have a polynomial time algorithm, and a problem is hard. Let's say if it's something that you know from the literature on the problem, you know that that's something that hasn't yielded to a polynomial time algorithm yet, and we widely believe that it does not have one. We do have good reasons for such beliefs, and I'll come to that in a moment, but for now let's just use this slightly informal way of referring to problems. And notice that you can have four kinds of reductions between easy and hard problems and the problem that you are working on, which I'm calling problem X. So you could reduce X to a problem that's known to be easy. You could reduce it to one that's known to be hard. You could also reduce an easy problem to the problem X, or you could reduce known hard problem to your problem X. So these are four kinds of things that you can do. And I would like you to pause the video here and really give this a thought. Think about what are the implications of each of these reductions. Assume that the reductions you have are valid. They transform instances of the source problem to equivalent instances of the target problem, pretty much the same way in which we have been doing for flows so far. So assume that you have valid reductions and that the reductions themselves are efficient. They run in polynomial time. What can you say is the impact of having reductions of each of these kinds? Okay, so I hope you had a chance to think about that. So whenever you reduce an unknown problem that you're working with to a known easy problem, then that's fantastic. You are in business because now you can take this reduction and then pipeline it into the algorithm that you already have for this known easy problem, and combined with the correctness of that algorithm and the ammunition you have from the reduction, which is supposed to produce equivalent instances, you actually now have an algorithm for the problem X. So this reduction basically amounts to solving X, which is very productive, and that's great whenever you can do it. So this is what has been happening all along with all the examples that we saw around flows. Now, if you reduce a known hard problem to your problem X, then that's the implication that we just discussed. You can basically turn the same argument around on its head to say that, well, now if somebody comes up with a nice, efficient algorithm for my problem X, then they have also, as a free byproduct, managed to solve this known hard problem. And if the hard problem has sufficient historical baggage, then you will be able to sell the idea that your problem is also a hard one. What you can say for sure is that X is at least as hard as the problem that you reduce to it. So depending on how hard a problem you can reduce to X, the more you will be able to say about the complexity of X. The other two reductions, unfortunately, don't really give you anything meaningful. They may be valid reductions, but if you reduce to a hard problem, then you cannot leverage very much about the hard problem and recover an algorithm for your problem. And if you reduce from an easy problem to your problem, then you cannot make any claims about the hardness of your problem, nor can you use the algorithm for the easy problem in a meaningful way. So both of these reductions are kind of in the wrong direction, so to speak. You can come up with them. There are several examples of valid reductions that go that way, starting from some problem and you reduce to a hard problem, or you reduce from an easy problem. It's just that these reductions don't have any immediate and useful consequences. So that's the main issue. To be able to talk about easy and hard problems, we probably need to define what we mean by a problem. So You probably have some intuition for what you mean by a problem. We often talk about optimization problems. For instance, you're always trying to find either the shortest path or the longest path or the maximum weight independent set or the best schedule. So most of the problems that we worry about are optimization problems, and we will be working with optimization problems later in this course as well. But to be able to define the complexity classes that we will be working with, we will need to talk about decision problems, which are basically simpler versions of optimization problems. These are problems that have yes-no answers. So basically, it's a binary classification of all instances, and they're very closely related to their optimization counterparts. So for example, if you want to know if a graph has an independent set of size at least k, well, that's an answer to a question like that will help you solve the natural optimization variant of independent set, where you're trying to simply maximize the size of the independent set that you can find in a given graph. So once again, just to back up and recap a bit, the optimization variant of the independent set question would be the following. Given a graph G, what is the size of a largest independent set in G? And the decision question would be, given a graph G and a target K, does G admit an independent set of size at least K? That's a question that has a yes-no answer. Now, if you can answer the optimization question, if you have an algorithm for the optimization question, then you can very easily use that algorithm to answer the decision question as well. You simply find the largest independent set and see if it meets the threshold of K or not. On the other hand, if you have an algorithm that solves for the decision problem, you can typically, in most circumstances, use that algorithm to also solve for the optimization problem. You just have to run that algorithm several times for different values of k. You can, in the case of independent set, do a binary search on the entire range of k, which goes from 1 to n, and find the first value of k for which the answer flips from a yes to a no. So up to a point, you say, well, you have an independent set of size 1, every graph does. Perhaps yours also has one of size 2, 3, 4, and so on. But at some point, you reach a stage where you say, okay, I have an independent set of size 36, but I don't have one of size 37. And notice that this sort of output is monotone, so you can actually run a simple binary search on the target value k and solve for the optimization problem. So these problems are closely related usually, and you can go back and forth between them quite fluidly. But for the purposes of defining classes of problems, we are going to, for now, just stick to the framework of decision problems. And formally, you can think of a decision problem as simply a collection of bit strings. So every instance of, for example, independent set is basically a graph and a number k. The whole thing can be encoded in binary, and all binary strings that represent yes instances of the independent set problem are binary strings that belong to the language that we associate with the problem, right? So you can think of the independent set problem as just being this collection of binary strings that stand for positive instances of this decision question. Okay, so that's essentially every problem is a subset of the space of all possible binary strings. Now, here's a cool side note. If you think about what is an algorithm, well, any algorithm that you can think of can be, and in fact is finally encoded in some bit sequence, right? So when you write a program on your computer, it finally gets stored as a sequence of zeros and ones. So fix an arbitrary encoding of programs, pseudocode, or algorithmic ideas into bit strings, and you realize basically that every algorithm is actually just a bit string, right? If you have the proper mapping, then you can go back and forth between bit strings and algorithms. Not every bit string may correspond to a meaningful algorithm. Some bit strings are just garbage, but every algorithm corresponds to a bit string. And notice that every algorithm can solve at most one decision problem. So we can think of only algorithms that take as input instances of decision problems and output yes or no. So you cannot have the same algorithm solve for two different decision problems, which means that any algorithm is good for at most one decision problem. And therefore, because the algorithms is simply bit strings, but problems are subsets of bit strings, you probably know from your set theory classes that these are just two different cardinalities of infinities that we are staring at. So in fact, there are strictly more problems than we can have algorithms. And in fact, this means that there are lots and lots of problems out there for which we will simply never have algorithms. And that's a very interesting field of study on its own right, but it's fairly out of scope for our discussion. So we are going to just come back to the more mundane affairs of problems that do admit natural algorithms. I just find it fascinating that there are so many problems, in spite of the fact that the space of problems is so much richer than the space of algorithms. It's pretty cool that most of the problems that we encounter actually do have algorithms that we can work with and that we can hope to optimize. So what are these problems? Well, we are going to use the notation P to talk about problems that admit algorithms that solve these problems and that run in polynomial time, even in the worst case. And we expect these algorithms to always be correct on all possible inputs. So when we say an algorithm solves for a problem, it always does it correctly. There's no margin of error. And it does so in worst case polynomial time. So any problem that admits such an algorithm, that would fall in the class P. So for example, you could think about decision variants of problems like spanning tree, shortest path, and things like that. All of that would fall in P. So P stands for problems that can be solved quickly. And we also have this closely related class called NP, which, well, it's very tempting to think of NP as not polynomial, and that's a fairly common misconception, but that's not what it is. NP stands for what is called non-deterministic polynomial, and that nomenclature goes back to the fact that these are modeled after non-deterministic Turing machines, and again, if you know about them, that's great, but a discussion about non-determinism in Turing machines is again going to be a bit out of scope for us. So I will focus on a simpler self-contained definition of the class NP. So NP consists of problems that have efficient certificates of verification. That means that a problem is an NP if you can basically verify a solution to this problem in polynomial time. So let's take an example. Suppose you're thinking about, again, the independent set problem, and I have an instance of the independent set problem. I have a graph G and I have a number K, and I want to know if this is a yes instance or not. I may not have the means to solve it, but let's say you come to me confidently saying that this is indeed a yes instance. Then I ask you, how can you be so sure? Well, you can point out to me a collection of k vertices that form an independent set, and I can go over those k vertices and manually verify that all of them are mutually non-adjacent. So that will only take me roughly quadratic time in k to just run through all pairs and check that they are all non-adjacent. So that's straightforward. To do it only takes polynomial time. So basically these are problems whose solutions can be easily checked. Now the first time you hear this definition, if this happens to be your first time, you might wonder if this is somehow too easy. You might think, well, don't all problems admit such easy checks? Surely somebody comes up with a solution that should be easy to check. But it turns out that that's not always the case. So, for instance, think about the problem of confirming that the graph does not have an independent set of size k. That's a slightly different problem, seemingly very similar to the original one. But now my yes instances are actually the no instances of the original independent set problem. So I only care about graphs that don't have independent sets of size k. Now coming up with a certification that my graph indeed does not have an independent set of size k. This is not so easy because I can't point you to anything specific and say that, hey, look, there is no independent set of size k. This reminds me of a funny meme that was doing the rounds once, where somebody was trying to complain on Amazon that they haven't received the product that they ordered. And Amazon customer support said, well, can you give us photographic evidence of the fact that you haven't received the product? And that's hilarious, because how do you photograph something that doesn't exist? If it's a broken product, sure. But if you haven't even received it, well, the meme just had the customer photographing his empty hands. And that's kind of roughly the essence of the next complexity class that I want to draw your attention to. This is called co-NP. And co-NP is the class of problems that you can think of as being in the complement of NP. So these are the problems where the no instances have efficient certificates, not the yes instances. So when I flipped around independent set, notice I said that, well, the complement of independent set is the question of whether the input graph does not have an independent set of size k, which means that the no instances are the ones that do have independent sets of size k. So that's something that's easy to verify. So the no instances are easy to verify. So when you have a situation where you haven't received the product, that's a difficult thing to convince somebody of, that you haven't received a product. The complement situation is when you have received a product, and if you have to confirm to somebody that you have got it and perhaps it's damaged, that is something that you can easily verify. Okay, so those are our basic complexity classes. There are quite a few more that we will not have time to get into, and this is really enough for the purposes of the discussions that we are going to have at least this week. Let me just draw for you a picture pulled out of Jeff Erickson's book, which demonstrates what we think the world currently looks like. Clearly, NP is a superclass of P, because if you can solve a problem, that's a much stronger thing to say than being able to certify it. So you can convince yourself that P is contained in NP and P is also contained in co-NP. And we believe that that's what the Venn diagram looks like. But the reason we say that this is what we think is because we don't have a proof that establishes the separations that are implicitly implied in this Venn diagram. So for instance, you could ask yourself, if there is a problem in NP that certainly does not belong to P, which is to say that there is no efficient algorithm that can solve all instances of the problem correctly in polynomial time. Well, this is something that we don't know an answer to, and it's probably one of the most famous open problems in all of computer science for the longest time. So this is sort of a working belief, and just to be able to move on with our lives and get work done, we have this as a working hypothesis of what the world looks like. And one of the notions that is key to helping us make sense of this world is this concept of NP-hardness, which is a fairly imaginative concept. I think it takes some courage to even suggest something like this. So we are going to say that a problem is NP-hard if every problem in NP reduces to it. And what do we mean by a problem reducing to another one? That just means that we have an efficient reduction connecting these two problems, where the concept of a reduction is exactly as we have been using it in the past. A reduction is simply an algorithm which takes an instance of this arbitrary problem in NP, let's say y, and transforms it in polynomial time to an equivalent instance of the problem x, whose NP-hardness is being defined here. So we want to say that for all y that belongs to NP, there is an algorithm that can transform y to x efficiently and in a meaningful way. By meaningful, I just mean that equivalence is preserved. Yes instances of y are mapped to yes instances of x by this algorithm, and no instances of y are mapped to no instances of x. That's the concept of a reduction. And we want to say that a problem is NP-hard if every problem in NP reduces to this problem. There's, of course, no reason to believe that such problems even exist. But let's just take a leap of faith and speculate a little bit about the implications of the existence of problems that are NP hard. So, if a problem is NP hard, then if it can be solved in polynomial time, then notice that every problem in NP can be solved in polynomial time because of the implications that we have seen for reductions so far. You can simply chain the reduction that is guaranteed by the definition of NP hardness with the presumed polynomial time algorithm for x. That's the hypothesis here. You put these two things together and you get a polynomial time algorithm for every problem in NP. Now that's really substantial because, as you can imagine, NP is a massive class of problems and you knock them all out in one shot. So to say that a problem is NP hard is to say that solving it in polynomial time solves every problem in NP in polynomial time. And you can convince yourself that these statements are in fact equivalent. And therefore, NP-hard problems actually carry a lot of baggage in the sense that if you manage to solve them, the implications are going to be huge. And therefore, given all the history around lots and lots of problems in NP, which are famously not known to yield to polynomial time algorithms so far, basically solving a NP-hard problem seems like an Herculean task. Solving it correctly on all instances in polynomial time worst case just seems like that would be a really tall order. And that's why the working belief in the community is that NP-hard problems don't admit such algorithms. And therefore, if you have a reduction that reduces an NP-hard problem to your problem, then your problem also now joins the club and enjoys that same exalted status of being a problem that's unlikely to be solved in polynomial time. But of course, all of this seems like a lot of talk in the air because, where are these NP-hard problems? Do they even exist, or did we just make up a definition and go on a wild goose chase? And this, I think, is widely acknowledged as one of the most seminal results in computer science to say that there are NP-hard problems. So in particular, the satisfiability problem is an example of an NP-hard problem, and it was one of the first problems that was shown to be so, using a very elegant sequence of arguments, which are beyond the scope of our current discussion, but they would be very much in place in a theory of computation course. If that's something that you haven't done yet, perhaps you should look into it if this interests you. But that's where you typically find a proof of what's called Cook's theorem, which gives us this marvelous fact that SAT is NP-hard. And from here, you just opened up a whole new world of possibilities, because if you can now reduce SAT to your problem, then your problem is also NP-hard. Okay? So let's just get a bit of a feel for what these implications really mean. So suppose we have an implication that reads as follows. If I own the Harry Potter novels, then there is an alien in the NPTEL office. So let's say that that's an implication that's true. Okay, so the if-then statement you have a proof for. What can you infer from this? Well, notice that there being an alien in the NPTEL office is very unlikely. It's as unlikely as perhaps SAT having a polynomial time algorithm, right? And because we know that that's unlikely, from there we can conclude that probably I don't own these Harry Potter novels, right? So a reduction basically tells us that if this problem X, this is assuming that you have a reduction from SAT to X. So if X has a polynomial time algorithm, then, well, SAT can be solved in polynomial time. So that's the implication that we are looking at. And because we now believe that SAT cannot be solved in polynomial time, that would imply that your problem X also cannot be solved in polynomial time. So that's the essence of these implications. One might argue that we are just building a web of implications here. Ideally, we should know this for a fact as opposed to basing this on a belief. the idea that SAT does not have a polynomial time algorithm. But until such a time that we have a proof for this, I would say that it's generally agreed upon that there's very substantial evidence supporting the idea that SAT cannot be solved in polynomial time. I know the slides say circuit SAT, which is essentially a SAT variant written in a slightly different form, which is not hard to sort of go back and forth in between. And I'd encourage you to just take a look at the course notes for both the definitions if you haven't encountered them already. Now, let me also give you one final definition here, which is the notion of NP-completeness. So a problem is said to be NP-complete if it's both NP-hard and enjoys membership in NP. So this is our updated Venn diagram. There could be some problems that are outside of NP and are NP-hard. That does happen. But most of the problems that we will be dealing with tend to be NP-complete, meaning that they are in NP and they also are hard for the class NP, meaning that all of NP reduces to these problems. So what we really are going to do for the rest of this week is actually look at concrete examples of reductions from a version of SAT which is called 3SAT. That's just normal satisfiability, but with the additional assumption that every clause has at most 3 literals. So the plan is indeed to work with 3SAT and develop these reductions to a bunch of other problems. And that's the plan for the rest of the week. And knowing what you know from our discussion here, you can then conclude that all of these problems also enjoy the status of being NP-hard. And if you think about it a little bit, you will also see that all of these problems also belong to NP. You can come up with efficient verifiers if you think about it for a moment. So although I will emphasize mostly the reductions and the aspect of NP hardness, these problems actually, the ones that we encounter this week are all NP complete, and I would encourage you to take that extra step of verifying that on your own when you have a chance. All right, so that brings us to the end of the complexity class recap, a little bit of terminology, and hopefully some clarity on what directions the reductions need to be in for proving what you want to prove. Always remember that to establish the hardness of your problem, you need to reduce from a hard problem. And to show that your problem is easy, you need to reduce to an easy problem if you want to do it by reductions. On that note, let's meet next time where we will talk about why independent set is at least as hard as 3SAT. See you then.